Welcome back. In this video, we will explore several questions related to simple harmonic motion to gauge your comprehension of the topic. However, before delving into this video, I highly recommend checking out my previous video on simple harmonic motion to ensure a solid foundation. In the previous video, we examined the dynamics of three specific examples illustrating simple harmonic motion. At the outset of the video, we established three distinct equations that elucidate the oscillatory behavior characterizing any system involved in simple harmonic motion. Additionally, we delved deeper into these equations, breaking down the details of angular frequencies unique to each example. This helped us grasp a better understanding of the core principles that govern systems undergoing simple harmonic motion. In this video, our focus is on applying these expressions to analyze more intricate systems. Our objective is to determine the specific angular frequencies associated with each of these complex instances. In this specific scenario, we delve into a system comprising two springs, each with its distinct spring constant, connected in parallel to a mass. This arrangement induces oscillations throughout the entire system on a horizontal plane. Our primary objective is to determine three crucial parameters. First and foremost, the resultant spring constant, which represents the effective spring constant of the combined system. Next, the angular frequency, intricately linked to both the spring constant and the mass of the system. And finally, the period, t, indicating the time taken for one complete cycle, inversely correlating with the angular frequency. Okay, let's examine a random position, denoted as x, in the oscillatory motion of the spring from its equilibrium position, and analyze the force acting on the system. Due to the distinct spring constants of the two springs, the restoring forces will vary, and we will designate them as F1 and F2. Firstly, we apply Hooke's law individually to each of the springs, considering the displacement as x at time t from the equilibrium position. It's important to note that this displacement is identical for both springs. Now, if we represent the net force acting on the mass as F, we can express F in terms of the specific restoring forces F1 and F2 associated with each spring. This relationship is shown on the screen. As we move forward and consider the net force F, along with the displacement x at time t, using Hooke's law, we formulate an expression that integrates the combined spring constant denoted as K. This step is crucial in encapsulating the joint influence of both springs on the system. Next, we integrate the expression derived from applying Hooke's law into the overall expression for the net force F. The outcome is a refined expression that illustrates the interplay of the individual spring constants and their collective impact on the system, as presented on the screen. What is presented on the screen can be utilized for a combination of springs connected in parallel, regardless of their orientation, be it horizontal or vertical. This equation is formulated with the assumption that all the springs share the same displacement from the equilibrium position. It serves as a succinct representation, illustrating the relationship between the overall spring constant and the individual spring constants linked to each spring within the parallel arrangement. Alright, moving forward, utilizing the derived stiffness of the combined spring system, we can articulate the angular frequency as illustrated here. This mirrors the discussion in my previous video, with the modification that we have replaced the spring constant of a single spring with the combined spring constant. Subsequently, we can calculate the period of oscillation using this expression. Let's proceed to the next example. In this particular case, we are exploring a system that consists of two springs connected in series, which is different from the previous scenario involving parallel springs. Much like our methodology in the previous example, we will ascertain the resultant spring constant, angular frequency, and period in the context of a series spring configuration. In this series configuration, each spring has its unique spring constant, and is attached to a mass, m, at the bottom. Importantly, the springs themselves bear no weight. This is the equilibrium position of the spring mass system. At this point, we assign the lengths of each spring as L1 and L2, serving as reference points for the system when it is in a state of balance. Next, we introduce a perturbation by stretching the combined setup, causing it to oscillate back and forth around the equilibrium position. This dynamic movement is visually depicted here. The combined spring undergoes a rhythmic motion, swinging alternately on either side of the equilibrium point. To analyze the behavior of the system at any given moment in its swinging motion, we select a specific point, and apply Hooke's law. This fundamental law relates the force exerted by a spring to its displacement from the equilibrium position. For our analysis, we define the distances each spring has stretched beyond the equilibrium position as x1 and x2 respectively. However, a notable point is that the tension in each spring remains constant, despite the variation in their individual stretches. This configuration introduces a new dynamic compared to parallel springs, and the analysis will help us understand the behavior of the system, in terms of its collective spring constants, and oscillatory motion. When applying Hooke's law to each spring, considering the individual spring constants K1 and K2, we derive two distinct expressions. These expressions highlight how the tension in each spring relates to its respective displacement. The variability in the stiffness values of the two springs is reflected in the distinct stretches captured by the expressions. The tension remains uniform due to the series connection, but the individual stretches are dictated by the unique spring constants. We can rewrite these equations as shown here. When considering the series spring configuration as one unit, the overall stretch is represented by the sum of the extensions of the individual springs. This combined stretch is denoted as X. We can formulate Hooke's law for this combined extension X, assuming a stiffness K, for the combined spring. It's crucial to note that the tension in the combined spring remains the same as that applicable to the individual springs. By leveraging the relationship between the displacements of the individual springs x1, x2, and the displacement of the combined spring X, we can establish an expression for the effective stiffness of the combined springs in series. This relationship is expressed mathematically as shown on the screen. Here, K represents the effective spring constant of the combined springs in series, while K1 and K2 are the individual spring constants for the springs arranged in series. The equation indicates that the reciprocal of the combined spring constant is equal to the sum of the reciprocals of the individual spring constants. This formulation provides a clear understanding of how the individual spring constants contribute to the overall stiffness of the series connected springs. This is a more generic expression for a combination of springs connected in series. The expressions featured on the screen outline the resultant angular frequency and the resultant period of oscillation for a system of springs connected in series. These mathematical representations encapsulate the dynamic behavior of the system, providing insights into how the combined stiffness of the series connected springs influences the oscillatory motion. Before we proceed with the video, I would greatly appreciate it if you could kindly give it a thumbs up, subscribe to my channel, and activate the notification bell. Your support means a lot. Thank you. Now, let's get back to the video. In the following example, we'll examine a system comprising 3 interconnected springs, shown on the screen. 2 springs are aligned in parallel, with an additional spring connected in series to this parallel configuration. A mass M is attached to the bottom spring as shown. Each spring is characterized by its unique spring constant, denoted as K1, K2, and K3. We'll apply the derived expression from the preceding section to ascertain the resultant spring constant, and the angular frequency of the oscillatory motion of the combined system. This table offers a representation of the values assigned to each constant mentioned in the spring configuration. We will use this data in the analysis of the system. We can't immediately determine the resultant spring constant of the entire system. Our first step is to find the resultant spring constant of the 2 parallel springs. To do this, We refer to the expression derived in the previous section, which enables us to calculate the combined stiffness of parallel springs. After applying the formula, we determine that the resultant stiffness of the two parallel springs is 2,400 newtons per meter. This value represents the effective stiffness, when the parallel springs are considered as a single unit. Subsequently, we proceed to analyze the two springs arranged in series. By applying the derived formula to this configuration of springs, we determine the resultant spring constant for the series arrangement. This calculation yields a value of 1,200 newtons per meter, representing the combined stiffness of the series connected springs. Once we have determined the combined spring constant for the entire system, we can proceed to calculate the angular frequency of the spring mass system. This frequency is a crucial factor that characterizes the oscillating movement of the system. By employing the given equation, we insert the spring constant we previously established, and the provided mass into the formula to determine the angular frequency. In essence, this systematic step-by-step process enables us to methodically ascertain both the resulting spring constant and the angular frequency of the system. In this example, we have a mass connected to two springs on either side, as illustrated visually. These two springs have different stiffness values. Initially, the system is at the equilibrium position, where the tensions from both springs are equal and opposite. This equilibrium state results in the mass remaining stationary due to the absence of a net force in any direction. To initiate motion, we displace the combined system to one side, and then release it, as depicted. This action induces oscillatory motion of the mass from left to right. This visual demonstrates how the spring force acts upon the mass. When a spring is compressed, it applies a pushing force on the mass, whereas when it is stretched, it exerts a pulling force. This continuous alternation between pushing and pulling by each spring in a single direction leads to the mass undergoing simple harmonic motion. With that introduction to the problem, let's proceed to calculate the effective spring constant and angular frequency of the system. We will consider the mass of the block as m, and the distinct spring constants as k1 and k2. To begin, let's identify any position of its oscillatory motion, and denote the distance from the equilibrium position as x. As seen in the previous visual, when one spring compresses, the other stretches. However, in this example, the displacement of both springs is the same. Nonetheless, because the two springs have different stiffness, the force applied on the mass from either side is not equal. Let's denote these forces as F1 and F2. Alright. Let's determine the net force applied on the mass, by summing up the two forces exerted by the two springs. Next, we will apply Hooke's law to derive expressions for the forces exerted by each spring. It's important to highlight that both springs experience the same displacement at any given time, whether they are stretched or compressed. Following that, we can develop an equation for the combined force by applying Hooke's law. The spring constant used in this equation corresponds to the resultant spring constant. Ultimately, we arrive at an expression for the resultant spring constant. This mirrors the spring constant obtained for the system with two parallel springs. Now, we can determine the angular frequency of the system using this expression. I recommend reviewing my previous video to understand how I derived this expression. I trust that the examples we've covered thus far have provided you with a solid grasp of the fundamentals of simple harmonic motion. Let's delve into a few more examples to further enhance your understanding of this intriguing field of physics. In this next example, we will examine the behavior of a spring mass system when the mass of the system is increased by adding another mass as depicted on the screen. It's important to note that there is no relative motion between the two masses when they come into contact. Our first task is to determine the angular frequency and the amplitude of the complete system when the mass is attached to it. This involves analyzing the dynamics of the spring mass system with the additional mass, and calculating the parameters that characterize its oscillatory motion. Once we've established the angular frequency and the amplitude of the system, our next step is to determine the maximum allowable amplitude, to prevent the mass on top from slipping over when the coefficient of static friction is mu. This analysis ensures that the system remains stable, and avoids any potential slipping or sliding of the masses during its oscillatory motion. The table provides the initial conditions of the spring mass system, prior to the introduction of the supplementary weight. By now, you're probably familiar with this expression for angular frequency. We will rewrite the expression for the new angular frequency, as displayed here. The only difference lies in the increased mass within the expression. We can also relate this to the initial angular frequency, as demonstrated on the screen. This expression will come in handy later when calculating the resulting amplitude of the system. Alright. In the context of the example we are discussing, which involves a series of activities related to a system with an increased mass, it's important to note the conservation principles at play. Firstly, we observe that linear momentum remains conserved throughout all stages of the events. This means that the total momentum of the system before any event is equal to the total momentum after the event, provided there are no external forces acting on the system. Additionally, we discuss the conservation of kinetic energy. In this particular example, kinetic energy is conserved through each step, as long as there is no initial velocity associated with the mass added to the system. However, it's crucial to recognize that in perfectly inelastic collisions, where objects stick together and move as one, kinetic energy is not conserved, except under specific conditions. In such scenarios, we rely on the conservation of linear momentum to understand the system's behavior post-collision or transformation. The expression displayed on the screen pertains to the conservation of linear momentum. By analyzing this expression, we can derive an equation that relates the final velocity of the system to its initial velocity. If we designate A sub n as the final amplitude of the system, we can express this equation in terms of the angular frequency before and after adding the mass, as depicted here. Substituting the derived expression for the angular frequency allows us to determine the final amplitude of the system, as shown on the screen. Next, we need to determine the maximum amplitude that the system can reach to prevent the added mass from slipping, considering the coefficient of static friction mu sub s. What's displayed on the screen is the free body diagram of the mass on top. For the mass on top to remain without slipping, it must satisfy this condition. We equate the normal force to the weight of the mass on top, since there is no acceleration in that direction. This results in the following expression for the frictional force. Now, we'll apply Newton's second law to the mass on top, and write down this expression. It's important to note that both masses experience the same acceleration, directed towards the equilibrium position, denoted as a at time t. After simplification, we arrive at this expression for the maximum possible acceleration, to ensure the mass remains without slipping. In simple harmonic motion, the relationship between acceleration and displacement is given as shown here. We can rewrite the above expression by substituting this relationship in place of acceleration. The maximum value for displacement is the amplitude of the periodic motion. If the mass on top remains without slipping, this condition should be satisfied. Previously, we derived an expression for the angular frequency of this specific spring mass system. By substituting this derived angular frequency into the expression, we can reformulate the equation for the maximum amplitude, as demonstrated here. Let's examine this example. The approach we need to follow here is quite similar to the one we previously discussed. However, I believe it will provide new insights to enhance your understanding of the subject. We're observing a mass connected to a weightless spring, initially stationed at the equilibrium position. This body is struck by another object with the mass moving at a constant velocity. Upon impact, the second object becomes embedded inside the larger body, and both objects undergo simple harmonic motion. Our task is to determine the angular frequency and amplitude of this periodic motion. Firstly, let's list the given information. I am sure by now you're familiar with the expression for the angular frequency of a spring mass system. Let's add the mass of the object that got embedded, and rewrite the expression for the angular frequency. This gives the angular frequency of the system after the increase in weight. If you're uncertain about how I derived this expression for the angular frequency, please refer to my previous video, where I provided a more detailed explanation. Next, it's essential to create an analogy that links the initial and final states of this system. Keep in mind that we are dealing with a scenario akin to a perfectly inelastic collision, where a moving object becomes embedded in a stationary one. In these cases, the total energy of the system isn't conserved before and after the collision. Hence, we must utilize the principle of conservation of linear momentum to determine the velocity of the combined mass following the collision. The equation displayed on the screen represents the outcome of applying the conservation of linear momentum. This calculation will yield the velocity of the unified system. What's displayed on the screen is the generalized representation of the velocity of an object experiencing simple harmonic motion. At the moment of impact, the mass was positioned at the equilibrium point, resulting in a sign value of omega t equal to 1. This provides an expression for the initial velocity in relation to the amplitude of the oscillation. By substituting the previously derived formula for the angular frequency, we arrive at this expression for the amplitude. The negative sign can be disregarded as we are solely concerned with the magnitude of the amplitude. In this particular setup, we're dealing with a spring mass system that features a unique arrangement. Instead of the conventional single spring, there are 3 identical springs, all with the same spring constant, attached to an object with a mass. Notably, these springs do not themselves bear any weight, rather, they are responsible for facilitating oscillation along the vertical axis, as demonstrated visually. For a more thorough grasp of how this system functions, creating a schematic diagram illustrating its initial setup, when the mass rests at its equilibrium point would be advantageous. It's crucial to emphasize that the 2 springs positioned above the mass are inclined at a 45-degree angle, relative to the vertical axis. Now, let's delve into the system's behavior at a specific moment, considering an arbitrary position characterized by a distance x from the equilibrium point at time t. At this point, the change in the mass's position induces tension in all 3 springs. What you see on the screen is the free body diagram of the system. This displacement of the mass causes compression in the bottom spring. At the same time, the 2 upper springs experience stretching. Although the change in the angle formed by these top springs with the vertical axis is minimal, it can be represented as delta theta. By taking into account this change in angle along with the displacement x of the mass, we can determine the extent of stretching in the upper 2 springs, as illustrated here. Okay. Let's apply Newton's second law to the spring mass system in the direction indicated on the screen. Mind the displacement and acceleration directions, and make sure to use the correct signs. This equation leaves us with 2 unknowns, t sub 1, and t sub 2. We can employ Hooke's law to work out expressions corresponding to these tensions in the springs, as displayed on the screen. Let's substitute these values for t sub 1, and t sub 2 into the preceding expression and simplify it. We can disregard the delta theta as it is too small compared to the total angle. This is the expression you get after simplification. This expression aligns with the equation for simple harmonic motion, where the coefficient of displacement provides the angular frequency. Keep in mind that the coefficient of acceleration should be 1. This example wraps up our discussion for this video. However, I'll be continuing to explore more examples on this topic, and sharing them on this channel. If you find this type of content valuable and enjoyable, I encourage you to subscribe to the channel, and hit the notification bell to stay updated on new uploads. Additionally, if you think this content could benefit your friends, please don't hesitate to share it with them. Your support is greatly appreciated. Thank you. In this specific scenario, a weight is attached to a string passing over a pulley, with the other end of the rope securely fastened to a stand. Additionally, the pulley is suspended by a spring with a spring constant denoted as K. Both the string and the mass bear no weight. Our goal is to determine the angular frequency of the mass in this setup. What you see on the screen is the mass at its equilibrium position. Let's proceed by pulling the mass downward, and then releasing it, initiating oscillations around the equilibrium point. Let's focus on an arbitrary position x distance away from the equilibrium position. This allows us to analyze how the system behaves, as the mass deviates from its stable point. Next, we need to determine the displacement of the pulley relative to the displacement of the mass. Imagine a setup where a rope passes over a pulley, but there's no weight attached to the rope, and both ends of the rope are securely fastened to the base. Now, let's say you decide to modify this setup by removing an equal length of rope from each side, and then clamping the ends back to the base. When you do this, the pulley will descend by a certain distance. Now, it might seem intuitive to think that the pulley would descend by only the distance that you removed from each side of the rope. However, it's crucial to recognize that the total length removed from the rope is actually twice this distance. This is because you're effectively shortening the rope on both sides, so the total reduction in length is doubled. It is with that understanding that you need to approach this problem. When there is a weight attached to one side of the rope, and the other side of the rope is attached to a base, when you pull the side with the weight down by a certain distance, the pulley will descend by half of that distance. Let's mark the distance descended by the pulley as shown on the screen. Simultaneously, we can identify the acceleration of both the mass and the pulley by taking the second derivative of displacement, as illustrated here. Since the pulley and the rope are weightless, the tension on either side of the rope remains the same. To determine the tension applied to the spring, we turn to Newton's second law. Since the pulley and the rope are weightless, when we apply Newton's second law to the pulley, the right side of the equation becomes 0, simplifying the equation as shown here. In a subsequent video, we will delve into how to handle similar systems where the pulley does have a mass. This introduces additional complexities that require a more nuanced approach in our analysis. Stay tuned as we explore these concepts further. We can now utilize Hooke's law to derive an expression for the tension in the spring. Substituting this expression into the previous equation, we can obtain the expression for the tension in the rope. The next step is to apply Newton's second law to the mass. It's crucial to emphasize that we disregard the weight of the object in this analysis. At the equilibrium point, the spring force counterbalances the gravitational force, resulting in a net force of 0. Thus, in this scenario, the combined effect of gravity and the spring is unified under the tensional force of the spring. Consequently, gravitational forces are not included in this expression. I have extensively illustrated this concept in my previous video, so I suggest reviewing it for additional clarity. We can substitute the expression for the tension in the rope, and represent it in this form. Interestingly, it closely resembles the expression for an object undergoing simple harmonic motion. By relating it to the standard format of the equation for simple harmonic motion, we can derive an expression for the angular frequency. Thank you for watching this video all the way through. I hope these examples have helped you grasp the concepts of simple harmonic motion. If you haven't subscribed already, please consider doing so to stay updated on future content. Until our next video, take care, and goodbye.